very much for the invitation. Yeah, I'm going to speak about knife and uncertainty in finance and economics. So, in the first talk, you already had a nice introduction by Ekaterina to the topic. I will focus in the middle part on the technical details a little bit. But feel free to ask in between if you think that it's getting too technical. So the talk is going to have three parts. Yeah? So one is what is financial mathematics, because I think that in the light of the financial crisis, it's really extremely important to explain what it is and what it is not in particular, no? And just to have a clear ground to discuss them. Then I will speak about knife and uncertainty. There will be an overlap with the previous presentation, of course, but with slight differences. And then I put the two things together, let's say, yeah, and speak about model uncertainty in finance and about some topics of regulation that were related to the start of the financial crisis, but that are not well known to some extent. Yeah, and but I think that some of the technical details are actually as important as other things that have been widely discussed in the literature. Okay, so I start with my first topic, what is financial mathematics? Now, if you take finance textbooks of the 30s or so, then it wasn't considered a science really. Yeah? So it was a collection of simple rules, so some sort of accountancy and so on. But they didn't take it seriously at research universities. But all that changed with the 50s, when the capital asset pricing model came up, for example, Tobin, Markowitz, these names. And then in the 60s, the real revolution started. And the names that you might think of, Paul Samuelson, Fisher Blake, Burton, yeah, for example. And what these people did, they tried to understand what can be said about financial markets with the help of probability. And okay, so Fisher Blake, yeah, so, who passed away before getting the Nobel Prize, unfortunately, yeah. But what he tried to do is, and you don't have to understand this, yeah, but he tried to understand capital asset pricing with the help of Brownian motion. And for some reason he came up with this formula. No? This is related to the partial differential equation. This is the value of some option, and here you see partial derivatives. And in my opinion, yeah, but this is just my humble opinion, this is the reason why many economists somehow shied away from the theory. Yeah? Because the theory, for some reason, started with a very complicated partial differential equation. Also, that's not necessary at all, actually, to understand the things. But that's how it came about. Yeah? And indeed, even Black and Scholes, in the beginning, it wasn't clear to them what they had discovered. It really took 20 years to understand completely what this means. Yeah? But it had immediate impact on financial markets. Why? Because it's a formula about a value of something, yeah? And there's no utility function involved. So something that practitioners don't like utility functions because they don't know what utility they have and so on. And here you have only observables, yeah? Interest rate, time, interest rate again, volatility. So volatility is something that you can estimate. Yeah? That's why the practitioners like it a lot. And that changed markets tremendously. So that you can consider really this as one of the biggest scientific revolutions in the 20th century, I think. But if you want to understand it, it's actually, you can go back to an extremely simple example, and I want to go through the example with you together, yeah, and see if it's clear what's going on. And then, because I will use the example to explain what finance is. Maybe you know it already, yeah? If you know it, okay, fine. Also better, yeah? The picture is a little bit smaller, I hope you can see it. So I don't take Brownian motion, I take a very simple model of an asset class. So today the value of my asset is 100, and then I assume that it can go up and down. I can also do it in the coordination. So make it a little bit bigger, yeah? So this is my simple model, which of course is not wrong, yeah? It's not correct. I mean, the world is not that simple, of course. There are more states than 2. But let's take it like this. Yeah? So 100, and you can go up to 105, and I can go down to 95. That's my risky asset. Okay. And then I call this the atom of finance, yeah, because it looks really like an atom, and this is really the thing that you build up everything with. And what finance does, now I take a bet. Yeah? A bet would be something like an option, but let me call it just a bet. Yeah? So you get 10 euros in this state of the world, and you get 0 in this state of the world. These things are usually traded in financial markets. They're called digital calls, for example. Yeah, you can buy them. If you know the Brøe arrow, so this is also called an arrow security, you know, in economics. And now the question is, what is the correct price? Yeah, how much do you pay for this? 10 and 0. Yeah? Okay, now you can guess. Yeah? So I can ask you, how much do you pay for this? 10 and 0, how much would you pay? Okay, not 11, I guess. No. Not 11, okay. And more than 0 maybe, no? Yeah, so that's pretty clear. And the classical economic answer would be, it depends on the demand and supply somehow, no? But it's not correct. Okay, there's only one answer, it's 5. So you must pay 5, else you make a mistake if you don't pay 5. Okay, and this is the basic insight of finance. So, and I want to explain this a little bit. Let's see, why is it 5? Yeah? So I do it on the blackboard. Huh? So, the idea is the bet, yeah, which is 10-0, is equal to a portfolio. Okay, portfolio with X shares plus Y cash. So just money, no? And let's see how we can do this. If I buy X shares, and you see X shares plus Y cash gives me 105 times X plus Y, and here it gives me 95X plus 4. And now I want this to be equal to 10 here and to 0 here. Yeah? 2 equations, 2 unknowns. That's good, no? So this is basic linear algebra. I don't know, you can take here the X should be equal to 1, I guess. No, if X is equal to 1, then Y must be equal to that's correct, minus 95. Yeah. As you see, if I plug it in, it fits perfectly. So, okay, you have to borrow money, yeah? 95 euro, and you buy one asset. And okay, so how much money do you need then? So what is the value of your account at time 0? Yeah, it's 1 times 100 minus 95 is 5. So that's why the only way to deal with this is to say, I pay 5 for it. If you pay 6, I can make money on you. Yeah, because you pay 6, say, excellent, that gives me 6, and then I do this thing at a cost of 5, and I have a gain of 1. So this is okay. That's finance actually. Yeah? So nothing else. So finance is not predicting the future or speculation. It's actually computing something backwards. Let me see if I get it. And then, of course, what mathematics is doing, with the help of mathematics, now you iterate this. Now you build a tree and so on, make it more complicated. You get Brownian motion in the end, and then you have a very realistic model to some extent of the world. But actually, it's also important, this finance model, you see two variables, 2 equations, works only in this model, in the so-called binomial tree. It doesn't work if you have 3 or 4 branches. That's important to understand. And so you get Brownian motion, and it works quite well in this framework. So in this sense, you can say, let's start here with the thing here down here. Good finance is the computation of today's prices for risky things. So what you do is you compute backwards, you never compute forward. So, I don't know, maybe you know this when you are a professor, or then sometimes people tend to ask you, where will be the DAX tomorrow? Yeah, and I always say, I don't know. This is not what I can do. I can tell you something else. You tell me what your bet is, I can tell you how much it costs today. So the other way around. So good mathematical finance is actually insurance. Yeah? How much do I have to pay to insure myself against the future risk? That is what good finance would be. And it computes hedging strategies. That's why it has been so successful. Yeah? So it provides really a recipe how to insure yourself against future risks. And what it is not, and this is what to some extent went wrong in the banks in the last years, it's not the prediction of prices, and it's neither the calibration of complex models. So calibration of complex models, what is that? Yeah? Calibration of complex models means that sometimes this model here is too simple, maybe, yeah? And so let's say there's things like this, yeah? But then here maybe you have here some parameters, yeah? P and Q that you don't know. What you can do then is you can take past data and estimate P and Q. So this is called calibration. But calibration is dangerous, yeah? Especially in financial markets when you don't have stationary environments. And that's where we enter the world of model uncertainty to some extent. Yeah? So calibration works very well in natural environments, for example, or in environments where you have stationary time series, which is what you know from econometrics. But if you're not so sure about your stationarity, then you have problems here. Okay, so this is You feel free to, you can ask in between, no? So if you...
Let me please ask. Why is finance not betting?
Yeah,
don't you bet on the probability model you have? For example, that an up movement to 105 is equally probable to
here,
its down movement.
But you see, here in my model there are no probabilities, yes? So, you see, I did it without any probability. It was just linear algebra. And this makes the basic model very robust, actually. I don't need to know the probabilities in order to do this. It's very interesting. No? So the basic Black-Scholes-Merton world is really robust. And there's no betting involved here. No? So if this is the correct model of the world, then it's
because there is a probability, because 5 is the mean of 0 and 10.
Yeah, but there's no problem. 5 is just the correct economic price.
Yeah, but if I say the upward scenario is more likely, then maybe the price is 6.
No.
Not.
It's always 5. Even if this is it can be that the real world probability is 90% here, and 10% here. Then this wouldn't be the expectation, right? 100 would seem sort of wrong, but that's the price. So it's really independent of the real world probabilities for what we do here, this hedging. That's quite important. Yeah. You can, now of course I can invent probabilities that make this correct. So I can write here 1/2, then I get 5. No? And this is what is called the pricing measure. They use it a lot in the banks also. So the pricing probabilities. Yeah? So there's the market sort of has implicit probabilities for every event, but these probabilities are prices, not really probabilities, that correspond to the event.
Professor, let me have a question on these complex models, because you said that these methods failed with regards to these models. So you mean that these are these ABS, MBS, and
yes.
Stuff, securitization.
I'm going to come to it. Maybe I can explain it again then.
Okay, perfect.
Yeah. So, but this is sort of the basic hedging of options, in finance. And so here I come a little bit to what went wrong, in my opinion. This is not really. This model leads to Brownian motion, so to continuous asset prices that move a little bit like, like this. In particular, the model that works well does not apply to jumps. So, what is a jump? A jump is if you have an event like
Flash crash.
Yeah, a flash crash, or Russia says we default on our bonds. What happened once, or Greece is a problem. Then from 1 second to the next, the information comes, and then a lot of things have different value. So these jumps cannot be treated by finance. So what they did is, they did it nevertheless, as usual. So I mean, to some extent, of course, you can still build a model, but you are beyond the world where everything works very well. So what you do then when you go to credit risk, you have here sort of these jumps, that you cannot accommodate. Okay, so you take sort of some new parameter, lambda. So that would be the beginning of the complex model. Lambda would be sort of the probability that bankruptcy happens, but you don't know lambda. That's the problem. So this is, and then you have to estimate lambda. You can do it on past data, of course. The problem is that there are not so many data on bankruptcies, especially of countries in the Eurozone or so. So then you start moving into a world where your model becomes uncertain, really, again. Before the model, I would say the basic model is quite robust. But here, if you start having a lambda, then you are in a risky world. Okay, what is done in the banks, which is not always bad, of course, but what you do is this lambda here predicts a price, and then you can fit it to the market data and find the lambda that fits best to the market data. That's again a calibration, and that's what is done in the markets typically. But this is different from the classic finance approach. So here we are now at nitrogen uncertainty, and this is explained already, but I explained to some extent again, and you can see. So this is sort of my decision theoretic explanation of nitrogen uncertainty. So in the decision theory literature, they decide typically between roulette and horse races. Roulette is where you have something like a machine, which is random, and everybody agrees that the probabilities are known because by experiments you can figure out that really you have a uniform distribution of outcomes. Then you have a roulette, and you have probabilities. Horse race, they like to take this name because in a horse race you do it once. The horses it's very difficult to predict how good they are. To some extent, you know, of course, you have some estimates, but there's no law of large numbers and so on. So typically you shouldn't have probabilities, but you can, of course. What is good actually about a horse race still, in contrast to what you said, at least you know the outcomes. Alright, outcomes is easy. If you have two horses, either horse 1 wins or horse 2 wins. So at least the set of outcomes is fixed. So the difference is, do you have probabilities or no probabilities? And here comes now, so in red now is always the mathematical part for the experts who like to know. It doesn't matter if you think that you're not so interested in these details. So, but in the spirit of the previous talk, so is in probability you have a P, you know the probabilities, you assume this, and if you have nitrogen uncertainty, there is no P. That's the important thing. There's just S, like state of the world. You don't know what is going to happen. Now, what is a classical economic approach to this? It has been mentioned before. Savage, for example, the Foundations of Statistics, or Enscombe and Aumann in the famous paper. They say, but if you are rational, you have probabilities. It's the usual approach. It's sort of a little bit, of course, an heroic approach, but you can say, okay, under some assumptions, you must have probabilities. How does it work? I asked you. Okay, so you didn't want to say what your price is, but normally the trick of Savage would be, I ask you a lot of questions. questions, yeah, and then you say, I bet on this and I don't bet on this. And if I'm allowed to ask you like 200 questions, yeah, then I can tell you afterwards what your probability was. That's the idea. If you're, of course, this works only, typically humans tend to contradict themselves, it's problem, you know, because they're not perfectly rational. But if you're perfectly consistent, then indeed, yeah, if I'm allowed to ask you enough questions, then I will find out if you have exactly one probability, even if you're not aware of it. Yeah. So this is Savage's and Anscombe Aumann's approach to probability theory. They say you have a preference relation, yeah? So, and I ask you, do you want to bet on A or do you want to bet on B? And this is your private version of probability. And you have it. Yeah. This is also the standard approach to...
So are these questions just decided, could you decide for B? Questions like this? Or?
Yes, yes. Well, I have to put also numbers here. Yeah? So if I really want to find out the exact probability, then first I ask, maybe I will put an example. I think I have an example on the next slide, yeah. This is my private example, that my contribution to literature here. Okay, so you see, I don't know, maybe you feel better when I ask you all the time, but here's the thing that you can bet on, yeah? The tennis is good, Giants win the World Series. You know what it is?
Not really, but...
Yeah. That's very good, that's very good. But you know what Arminia Bielefeld is and Pokalsieger 2015, no? You see? And this is a typical question of Knightian uncertainty, because you know sort of the states of the world, but it's very difficult to assign probability to both things, actually.
I think the second is probably...
The second is, for most people, they're pretty sure that this is zero. But nevertheless, okay, so maybe I should, what should I write? Dortmund? Yeah, Dortmund, we're close to Dortmund here, so. Yeah, no.
No, I will postpone it.
Yeah, so let's say Dortmund is maybe better because it's far away from zero, yeah, so, and then if I ask a German soccer fan, what do you want to go for, then it's perfectly rational to say I have no clue about the San Francisco Giants, so I bet on Dortmund, okay? You have to decide that. Yeah.
So we have to decide between those two things?
Yeah.
But they don't have anything to do with each other.
No, but you can get 100 here or 100 there. You don't have to pay. For the moment, so.
Great night.
And so that you just have to say what you find more interesting. Yeah? And now I turn it around and I ask somebody else. Yeah. So San Francisco Giants do not win the World Series, and Dortmund wird nicht Pokalsieger. Okay. That is exactly the compliment. And then just because you still have no clue what the San Francisco Giants are. You again take this because there's Bayern around and so on, there's a high probability that also this will happen. But if you do this, you violate the laws of Savage. Yeah? Because if you bet on this, here you say the probability of this event is higher than the probability of this event. And at the same time you say, again, then you go for Borussia Dortmund here, then you say that the complement is a higher probability than the complement. This cannot be. Still, it seems very plausible to many people, and this shows that the Savage theory of subjective probabilities is a strong assumption. Yeah? So it is, and therefore my conclusion would be that it's even rational. Yeah? It's even rational not to be additive. Rationality does not necessarily imply that you must have probabilities. Okay, last thing, the San Francisco Giants sometimes win the World Series, it's in baseball, yeah? So, okay. But very rarely also, so it's probably Arminia Bielefeld fits. Okay, so, yeah, this has been mentioned before, I just wanted to say it again, but so the famous, it's called Knightian uncertainty, goes back to the thesis actually of Frank Knight. It's a book called Risk, Uncertainty and Profit, and what he says is many economic decisions are of a one-shot nature, like a horse race, and it's difficult to assign probabilities at least. But nevertheless, I mean, I think that, of course, there are things out there where we have the right to assign probabilities. Yeah? Typical examples would be some insurance examples, car insurance, life insurance, for example. Why? Because here you can assume that the car accidents are more or less independent across individuals. If I have a car accident or you should be rather independent. But the law of large numbers, yeah, and the central limit theorem, you can be pretty sure that you have control over the probabilities if you have enough data. Same for life insurance, yeah. At least if you just think about mortality, we have mortality tables, they're pretty good. Also there's a certain model uncertainty, but at least you know that, for example, most of you in the room, those around 30 or so, yeah, they have a very low hazard rate to die this year. No? And then, of course, after 70 or so, it goes up. No? IBM, why have I written IBM? Because IBM stands for a long-established company where you have a lot of data about the past and maybe a good idea of the returns. Still, yeah, it's sort of riskier because they're in a changing environment, and then in this IT world where a lot of things happen all the time, management plays a role and so on. Nevertheless, these are maybe equities where you can try or trust statistical models. And then there are, of course, other things where we would hopefully agree that it's less clear. Yeah? So, very difficult thing, for example, is market entry. So when a new firm enters a market, it's a typical economic question, of course. Yeah? So close to Bielefeld, we have Bertelsmann, and we talked to them for once, yeah, and they wanted to have a mathematical model for market entry in India for certain thing. And of course, there are economic models there, but indeed, we were also very reluctant to really make a prediction, yeah, because the fact that a company enters a market changes, of course, the environment in such a dramatic way that you're not so sure if you can rely on the statistics of the past. Another example are startups. When you have a new company like Google 15 years ago or so, it's very difficult to know the probability of the return. Yeah, that's clear. One of the big issues in the financial crisis was, of course, that they did the following. This lambda here, yeah, lambda, corresponds to a rating, and the ratings of the agencies were objectivized in a certain way. So what they did is they took the ratings by the agencies and assigned probabilities to them. Exact probabilities, yeah. So like BB would be something like 1% probability that you go bankrupt this year. B is close, it's a very bad rating already, no? But then later it turned out that all these probabilities had nothing to do, of course, with reality. You know? So that's where model uncertainty comes in. Of course, the rating BB is qualitative anyway. You know? So it was a mistake to assign numbers to this. This is agreed upon, I guess, by now. So, and now I come a little bit, so here comes what you announced, that it's going to be a little bit formal. In decision theory, there are formal approaches to such model uncertainty, and I want to explain them a little bit. So one goes back, they're all based actually on something that is called robust statistics. So Huber is the name, it's really a nice textbook on it, if you're interested. But in economics, there are two main models. One goes back to Bewley, and the other one is Rieber-Schmeiter, that you mentioned. So it works as follows. I don't know, I assume that I don't know the probability, but I stay to a certain extent in the framework. Yeah? So, of course, you can still question this and say, it's not enough. Yeah? So if you should do something completely new, this approach is rather parsimonious in that sense that we stay relatively close to our standard model, but we allow for some range. That's how it works. So, that makes it very formal, but you see here what the difference is. Instead of one probability, I work with an interval. And then I say, okay, X is less good than Y, if in all worlds, in all P, the expected utility is smaller for X. That's what Bewley proposed. And Gilboa-Schmeidler have a sort of different approach, which is, in my opinion, slightly better, but they are closely related, of course. What Gilboa-Schmeidler do, they look at the worst case. So you still have a set of probabilities, but you compute the expected utility and the worst case probability. Worst case analysis is well known in economics, of course. You can, it's sometimes called the Wald criterion after Abraham Wald, who simply used max-min in an extreme sense. So if I take all probabilities here, then I just look state by state and check the worst case. This would be the classical max-min approach. And this Gilboa-Schmeidler approach can be seen as a sophisticated version of max-min. So in my tree, so here are the probabilities of economic.
Schauen Sie.
Gibt es da Stifte? Sollen wir das one or?
Können Sie da auch benutzen, ne?
Ja, genau. Also so. What you do is essentially this, yeah. Instead of working with 1/2, you say, okay, the probabilities will be between 1/3 and 2/3. You give a range. Then, of course, the next question that I always get at this point is, who tells me the size of the interval? This is true, yeah? So this is still part of the modeler. It's a decision by the modeler. But it makes your decisions more robust, you know, to cases that you might not have considered before. Okay, like it or not, yeah, it's up to you, of course, to think about this. No? This is a large literature by now in economics already, so especially the Gilboa-Schmeidler model has been studied a lot, and a lot of things can still be done. That's why people like it a lot. Yeah, so you can still build a nice theory of economic models. So now I'm coming to the third part. I want to apply this a little bit or show how it can be applied to some problems of regulation in financial markets. So we change the color, yeah, so it's the third part of the talk. But I come back, yeah, so you have seen this before. And now I agree it's technical, but we're still in the same spirit, yeah. So we have no probability, there's no P. And an uncertainty measure in finance is now called something like this, and you can, yeah, that's how decision theory works. You put some axioms that you agree on. So what is an uncertainty measure? It's some sort of expectation, but more general, yeah? So it's called, first of all, it should be cash invariant. So if I have a risk and I add some money to it, then it's the same as evaluating the risk plus the money. Okay? So money is, in a certain sense, saved. Then we assume monotonicity, and something that economists like a lot and which makes sense if you want to regulate a bank. You want them to like diversification, because when they diversify, they are more robust, yeah, to risk. So you don't put all your eggs into one basket. And this is what this concavity here says. So if you mix X and Y, then the value should be higher than if you just look at X or Y alone. This is concavity. Okay, and then then you can add homogeneity. You know, think of double sort of. Yeah, so this is nice, but maybe you don't. There's no economic reason, in my opinion, to do this, but it makes the theory much nicer. If you agree on this, yeah. So we can think about it. If we agree on this, yeah? Everybody for herself or himself, no? Monotonicity is okay, no? Diversification should be okay. Some people don't agree on it, especially now because there's no saved money left. Yeah, but as long as you have saved money, then this should be fine too. And then there's a theorem which tells you if every uncertainty measure looks like this actually. So now you have to just, I started with, okay, let's have the P's and so on. It was not so clear where they come from. Yeah? But actually the only way to measure uncertainty in this way, so if you believe my three axioms, you are here. Yeah? So continuous technical thing. An uncertainty measure has the form, we take the minimum over a set of priors, expectation of x. And this can be generalized but this is for the experts only. So what does this have to do with the financial crisis? Do you want to take notes or you look as if you are wrong or no?
I think we get your slides or.
Okay, yeah, if you like this. So now here's my, so you know, if you don't know Peter Bienara, it doesn't matter maybe. He's a friend of mine actually. He worked for Goldman Sachs. Now he's retired already, no? At 44. But he once told me on a party, yeah, all began with Basel II, and there's some truth. And he's not the only one who says this, yeah, but I like to cite him, okay? And there's some truth to it. It has to do a little bit with model uncertainty, and I want to explain this now. Okay, what was Basel II? This is Basel Committee for Banking Regulation. And in the late 90s, early 2000, they established these new rules for banking regulation. One big thing that really played a role is that from that point on, value at risk was used to regulate the liquidity of banks. Value at risk is not a utility function. Value at risk was invented by JP Morgan, by an investment bank, by statisticians there. And at first, it looks like a reasonable thing to do, but it's dangerous. Yeah? I want to explain a little bit why. But first, so if you look at the regulations, you can find things like this. Yeah, the minimum own capital that you need to hold is 8%. The additional thing, assets, yeah, plus 12 times value at risk. So this was meant to measure the risk of the bank or the risk of a position. Okay. Then of course, as a bank, it's great if this is zero, no? Then you don't need much minimum capital. So that's the point. And let's see what value at risk is. And maybe you know anyway. It works like this. It's really an idea from statistics, not from economics. That's part of the problem, in my opinion. So that what they do is they take a confidence level, let's say 1%, and then value at risk is defined as follows. The value at risk is $10 million if the probability to lose more than $10 million is alpha. If you remember your probability class, you know this is a quantile. Had they called it quantile, it wouldn't have made career in finance, I can tell you. So you need to call it value at risk. Yeah? If you call it quantile, then they don't. Sounds technical. No? So value at risk sounds better. So if you remember, yeah, so for example, let's say here's one, yeah. Let's say this is the distribution function of your profits and losses. Okay, then here's 5%. You go here. And here is, let's say here is minus 10 million. Then 10 million is your value at risk. That's how it works.
Where did the 12.5 come from?
Yeah, you
And why wasn't it an exponential function?
No, yes, that's a good question. So the 8% I happen to know a little bit is because this is traditional, they somehow agree on it, yeah, it's sort of a negotiation. 12.5, I have no clue, actually, the truth. Maybe 8 times 12 is 100, but...
I mean, from today's perspective, it would make sense to make an exponential function if we assume, for example, that when one big bank gets a problem, the value at risk of the others will not be linear, but also exponential.
So first of all, the problem is linear, okay, but it has to be easy, yeah? So you want to explain it too. On the other hand, yeah, but it's going to be even worse than that. So these numbers are negotiated. So now for Basel 3 or so on, they negotiate again how to do it. Of course, it is also critical, but more important, first of all, we want to understand what value at risk is. Yeah? So this is a very important number. And they all have to deal with it. Yeah? If you go to the banks nowadays, every trader has value at risk. They look at it. Yeah? So that's a limit, sort of. Yeah. So it's a quanta. What are the problems? Before I show you the slide, let me explain. First of all, yeah, you have to estimate these things. This is not so easy. Okay? So you have to estimate the distribution function. So what you have is estimation risk, or what this is model uncertainty, no? In its pure form. You don't know these probabilities actually. They're very difficult, especially in credit risk or so. They're extremely difficult to estimate. There's a large literature on this, of course, but nevertheless, it's difficult. So that's where the model uncertainty comes in. And let me see if I have another color. And then there's another problem. If I take another distribution function like this, and they happen to cross here, then they have the same value at risk, because I only care about this one number, yeah, where about the quantile. But they are very different economically. You see here the probability of losses are much higher in the tails. So, okay, so this is it goes under the name of sensitivity. Yeah? So value at risk is not a good measure of risk. Yeah? Value at risk does not see any risk which is smaller than this alpha. And then, this is why my friend Peter said that was a starting point for us. Once you understand this, yeah, you know how to trick the whole thing. Yeah? Because if you are now a trader, then you start playing around here. It doesn't change your value at risk, but maybe you can do something here and make profit from it somehow. This is let me see if I can explain this. I assume you see for some reason you are in the bond market or so, yeah. So with a very high probability of now we do it differently. I just write the probability, say 95%. You get 100 million, yeah, but there's a probability of 5% maybe that your counterparty is bankrupt and then you lose 10 million. Then your value at risk would be 10 million. Yeah?
But in this example, if we know with 95% that we can get 100 million, isn't there an opportunity cost in the value at risk? Why?
Value at risk is only measuring the risk.
Yeah, but I have the risk.
I don't see.
Okay. Okay.
So, how does it work? Now, I look at a different contract where you use 100 million with 2% and 10 million with 3%, and again 95% you get 100 million. Yeah? Economically they're of course very different, because with a very small probability you lose a lot of money, but the value at risk is the same. Because value at risk is the quantile, yeah? So when the probability crosses 5%, and this will happen here at 10 million. These two events together at 5%. That's what And then quantified risk takes this number. It doesn't look at the larger losses. It's silly, of course, yeah, once you have understood it, but that's how it works. Now, if you're a trader, then you can do the following, yeah. Instead of having this contract, yeah. So if you do this, yeah, you take a risk, no? And maybe your counterparty gives you a fee for it. It's like an insurance. So let's say they give you what would be the expected value here, 95. Yeah, they give you. Shouldn't compute this now. So whatever. How much would we pay for this?
Bisschen weniger als 95. Bisschen weniger als 95.
Ja.
Das ist nicht viel.
But here it's different, no? Here it's different. Because I have the 100 million here, so minus 2 million, no? So minus 2 in expectation here. I don't explain it very sorry. So what I want to say is, if a trader takes this risk, he gets a much better return. No? Okay, but the value at risk is the same because the counterparty is willing to pay more for this contract because they can get 100 million with 2%. They have insured a huge risk, and the trader, okay, is not hit because he looks only at the value at risk, but of course his company is hit, because if this happens, then the company is bankrupt. Yeah? So value at risk really sets the wrong incentives. Is it clear more or less? This example? I didn't explain it well, I think. Oh, it's okay? Okay, good. So, and now here we are at the asset-backed commercial papers, because this is essentially what they did. They used these CDOs, yeah, so credit debt obligations and asset-backed commercial papers, to hide things into small probabilities. So this is the problem. Can this be accommodated? Yeah, in my opinion, yes. Yeah. So can this be changed? And here is where nice uncertainty comes in. So instead of taking, well, I always run around with this message, but nobody listens so far. Yeah? So I don't know if anybody will ever change this. And I'm not, of course, not the only one. Yeah. So from an economic point of view, at least in my opinion, yeah, the better way to measure the risk would take this form, which is very similar, as you can see, to worst case analysis. Now we look at losses, not gains. That's why there's a minus, and we take the maximum. Yeah? Maximum over all losses over a class of probability measures. One can prove that this delivers a sensitive manipulation-proof measure. It's convex, so it encourages diversification, and in a paper with Ozan Danar, which is in economic theory, we have also studied the consequences on in equilibrium. Now you know that in equilibrium, okay, then of course we assume loss of rationality and so on, but nevertheless one can study these things. And it would lead to much less trade, of course. So the banks wouldn't necessarily like it. On the other hand, maybe we are happy for the moment to have less trade. But I mean, I have some students who work in the consulting business, and they always tell me, you cannot sell this, yeah, because it's too worst case in spirit, and worst case means that you become very cautious. This is of course a drawback. But it would be an approach to make the system more safe, more stable, in my opinion, and it would be a nice application, let's say, of this uncertainty theory. Then I'm already at my summary. So, good finance is insurance, and that was a starting point. So, mathematical finance should compute price of future risks and provide robust hedging recipes. And this should survive, of course. And this is a very important theory. Like with many theories, yeah, to a certain extent, with many scientific breakthroughs, it happened that it was extended too much. Yeah? And so this is what I would call dangerous finance, where we lose the robustness, and model uncertainty plays a big role. And we have seen a little bit how maybe one can deal with model uncertainty in financial markets. Of course, this remains to be discussed. The discussion is not finished yet, but there are also, I hope that I can convince you that there are also technical details that need to be covered, no? If you want to speak about the new regulation of financial markets. And maybe such uncertainty measures or risk measures would be a good tool to make the financial markets more stable. Let me stop here.
Hi. Do you have any questions, comments, whatever?
I have a question maybe to you in the first place and then also to the audience. What we are trying, among other things in our chair, is what would happen for economic theory and financial theory. For example, if you don't have this Archimedean point of a risk-free rate. So what happens if this is not existent? There's not much literature on that, and that's why we are interested.
Yeah, no, that's a very good question in my opinion. So there's a literature on it, no? But it's not read. But you know, somehow traditional economists ask the question. So in general equilibrium, for example, they were aware of the fact that there's no risk-free rate. Only in finance. No, in finance they never look at this. So they take it as granted that there is a risk-free rate. But the classical economic literature actually has this. Mm-hmm. And then a lot of things go through, so it's not the case that everything breaks down. Then it depends on the specific question at hand what the consequences are. But there's a literature actually on this.
And you had on one slide you said, okay, 1A is more favorable than 1B. What if you add, for example, a third option and which is not transit, that you don't have any transitivity, and it becomes, how to say, the theory becomes more messy but more realistic. For example, we prefer apples than oranges, and you prefer oranges to lemons, and lemons to apples.
Yeah, then you have no theory. But so in economics, of course, they always assume that you have transitivity. No? This is probably part of a certain type of rationality. You see, but
the apple rationality is also.
But you know this famous money pump thing, no? If you have these circles, it's like, a little bit like in this German story of Hans Glückner a little bit. So I can trick you. You see, because you prefer apples over oranges.
And oranges over lemons. And lemons over
apples. So you're always willing to give me money, no? And then, but in the end, you're back at the apples. You see? Right?
There is no end. There is no end.
There's no what?
There is no end.
It's
yeah, there's no end for you. No, if you have a circle, it doesn't. I trick you. I mean, you see, what did you say? Apples are better than oranges, are better than what? Cigarettes. So we start.
C is better than A.
Yeah. Okay. So you have apples, yeah? Okay. I give you some cigarettes, and you give me €1, okay? Because apples is much better for you. Then you have cigarettes. I give you oranges. You give me €1. And now okay, in the first place you gave me apples, yeah? So now I give you the apples. You're back at the apples and I've made money on you. That's the problem. And then I do it again. And indeed there's no end, but it's not so very fun.
Maybe your money.
Yeah, I agree that some people are like that, but then the problem is that you can be tricked. That is the problem.
He has no money.
Do you have any idea how you can get rid of the estimation problem you mentioned earlier on? So, because you always have to make some assumptions, is like scenario modeling, I assume this distribution, I assume that one, that one, that one, that one, and then I look at different distributions. Because it seems to me at least that just looking at one distribution is rather risky.
Yes, yes. So I think, but there are some experts here who do empirical work, they might know better. The first thing would be to work with a class of estimates, you know? And to give numbers, so like confidence intervals that show how risky the whole thing is at the moment. Mm-hmm. That would be at least a starting point. And then you should look at how sensitive your prices or whatever are if you vary a little bit the outcome. I mean, this is being done at the moment already a little bit. Yeah, this is what they call stress testing, for example. But yeah. So what I proposed here was some sort of worst case analysis, which would be the most cautious way to deal with this.
You said that you're working at an interdisciplinary institute. Much that is coming from financial mathematics and financial economics is very much in this equilibrium realm still, and much that is coming from the physics community, for example, these self-organizing systems and so on, is very much coming from far from equilibrium concepts. How do these people work together?
Sometimes they work together, as far as I know, but not. So the problem is that the basic physics approach has not been translated in a successful way into economics. Most physicists, when they applied their models, which are good, they treat banks like atoms, which is wrong, somehow, you see.
You treat agents also?
No, my agents are much more sophisticated. Anyway, but I agree, maybe that's a topic for, but then there's a bridge is needed, so it's not enough just to take a physics model and to reinterpret every term. I give just simple other names to it, then this is why it's not accepted at the moment from the larger economics profession. But it would be, I agree, it would be an interesting endeavor, no? And for example, one second or so. But there is an approach with, but I can, if you like, you write me an email. So some people are working on it. So at ETH Zurich and Hans Vollmer also, because they apply, if you know, these models from statistical physics, like the easing model, and they combine it with risk measures now. So this might be an interesting approach, but it's all in the beginning.
Yeah, this might be a little bit unfair because it's not exactly, I think, your field, but at least, I mean, if you look at the historical data, you can see that, say, for US, the stock prices over long periods of time tend to fluctuate so much that at the top, I mean, stock prices are approximately 200% has grown as much as the country's GDP, which in a sense, the country's GDP should be some sort of measure of how much the economy actually is growing and so on. And these fluctuations are extremely much more volatile. Yeah. You can also see, for example, in UK, the return on equity in UK was something like 6–7% on average up to say beginning of the 80s, possibly a little bit earlier, it started to increase. And since then it has been on average 22%, which also seems to be an extremely high return in an economy that grows with 2% per year. Yeah. So how can you understand, say, these the actual
it's very, I mean, I don't think that I have the definitive answer now to this, but maybe an interesting, so the classic economic answer would somehow be market power, no, sometimes. So how can you get returns that are somehow too big, no? One reason is market power, and okay, I didn't discuss this, but we have this to some extent in the financial markets, no? And So this would be one explanation. The other one is if you have the wrong regulation, you can cheat the regulation, as I tried to explain, and then you can generate returns on that too. To some extent, this might also explain the high returns.
For example, say during the last 30 years, I think it is partly because of the leverage, because that is what has happened. And that means, of course, I mean, an enormously much higher risk.
But that's, you see, that's what they did with value at risk. They could leverage their positions, and the value at risk didn't see it. And that's where I think, I mean, at least for the big investment banks, that's what they did. That's how they generated the 20% that Ackermann famously, the German CEO of Deutsche Bank, was famous for saying we need 20% return on equity. So that's the way to get it, I think.
Exactly.
I saw the question more. Sorry. Yes, it's your turn. It's more of a comment, not a question. Going back to the physics-related part, and this is just something that I'm adding from the last workshop on the reflexivity as part of uncertainty, and basically it would be maybe ideal, or we would want to have sort of a theory of economics with financial that it works on terms of like physics, or we would want them to work together. But what the main distinction that they mentioned last time is that when we deal with finance, we're dealing with people, and when we deal with physics, we're dealing with nature. And when we postulate a theory or something in nature, we may not be right, but the natural laws will not be changed, like they will work that way. But when we postulate a theory about humans, that might change the actions of the humans, and that's the problem where that's the problem where the uncertainty and the reflexivity comes, that you don't really change the nature. You might be wrong or right, you may never know, but with people you change their actions, and that gives a back feedback to the way you postulate the theory, and that's the problem. There's this distinction between physics and social sciences, and how it's really hard to reconcile them together.
No, I agree with you. But there, the economists would say that this sort of reflexivity or endogeneity, feedback effects, this is something that we know.
They put it in this common knowledge assumption.
But but nevertheless, if you take game theory, for example, then you would say, okay, this is typical for social sciences, and that's where we incorporate these things.
But how can you know how it changes your knowledge exactly, or your perceptions? That's hard to capture in a model.
No, this can be done. This can be done. Okay, so it would take us a little bit too far away, but in a game theoretic context, I would anticipate what you are planning to do, and so feedback would play a big role actually in the analysis.
Yeah, but there is an end of this feedback. You have this equilibrium strategy.
Yeah, in the end, of course, we converge to an equilibrium, and then.
And she says, until we reach this asymptotic equilibrium, a lot of things happen that change the equilibrium, so that we will never reach it, because it always is out of sight.
But I find this interesting. We can discuss it. So there's also evolutionary game theory, of course. So, but they try to deal with such things. But I agree that classic economics, of course, likes to converge to Nash equilibrium also. Maybe you have something that. Maybe I can make some. No, are we online here? No.
No, I'm not.
Yeah, okay. No.
But I can go online.
No. I wanted to run a commercial, but maybe it's. So if you're interested in these things, in Bielefeld we are going to have a summer school, in the summer, with the physicists also. You might check the web page.
Professor, so, or somebody
That
else?
was first, sorry.
Okay,
That's fine, go ahead.
Okay, don't fight this part.
Okay, so Professor, if I understood correctly, so the main problem of the value at risk indicator was that it didn't cover the risk of the fact that the price could have moved dramatically, and it could also have this problem with liquidity. Because according to the official classical economics, assume that liquidity is always on demand, yeah.
Yeah.
But in the times of uncertainty, it flies, yeah. So
Yeah, that's
basically, even if you are diversified, I mean, it doesn't help, yeah, because they all prices of the assets are moving, yeah. So they are basically lockstep, yeah, and that's why that was the case of the crisis, because basically like Bear Stearns or ING, they were very good diversified, yeah.
Mm-hmm.
I suppose that the so-called toxic assets, yeah, they had only like 7 or 8% of their portfolio, but they basically decided, about their survival.
Yeah. No, that's right. Correct description. I mean, uncertainty can lead to market breakdown. So, in a certain sense.
So may the stress test help you in this case?
Yeah, we are not sure. We are not sure because here in this, in the study that we did with Roland Dana, here I have it here. This is here. This paper here. It's difficult to find in there, yeah. But the stress testing can have also negative effects, and one effect could be that the banks don't trade with each other anymore. That's what we see a little bit also at the moment. They are so reluctant to get bad credit that they stop trading. It's also bad for the economy.
And they are worried about the liquidity, basically. That's why they're doing it.
Yes, yes.
If you jump back to your equation, you say you want to replace the value at risk one, the min-maximum equation.
Yeah.
So this also may not be your area, and I suppose we're going to discuss this generally for the rest of the next couple of days. It's not that one, but similar. But the one with the negative. The point is that you're saying that it's better to replace the at-risk rate with this maximum equation in which you maximize over these probability distributions. The issue, obviously, is that kind of, with uncertainty generally, you're just kind of kicking it down the track to, you have to then determine those probability distributions yourselves, which then is, can you see any, and the problem with the risk-free rate is that it's a quantile, and so it can be manipulated. Is it possible that simply the reporting of then those probability distributions that you maximize over are also going to be manipulable by agents? I mean, because largely those distributions are going to have to come from the finance industry itself, and obviously the traders that they're going to make money out of necessarily, you see what I mean? So there's still going to be a kind of a feedback in which is incentivized to report possible probability distributions badly to then.
So within the model, within the model, such an approach gives the right incentive. So you don't want, actually, it's not in the interest of the agent himself to manipulate. So that's good about it. Of course, this is within the model, as usual in economics. So once you fix the model, you can prove that the agent does not want to manipulate. So, and which is not true for value risk. Of course, then the meta question that you ask is...
The second question is what you just kick the uncertainty down the track.
Yes. No, to some extent, yes.
And so basically, so then you're just kind of minimizing over lots of possibilities to try and spread the uncertainty. Is that the kind of idea? But I'm wondering if that works. I suppose philosophically.
No, that's a critical question, and probably, as they say, proof of the pudding is in the eating. No, so one would need to check it. No? And I wouldn't say that this is the only solution or so, but it deals with some issues, let's say.
And also the other issue that I thought about is that the bonus of the quantile risk-free thing is that, as you said, it's a much easier measure to have, right? You're choosing a quantile. Whereas this one, you're trying to minimize over a lot of probability distributions. And getting probability distributions is far more complicated, especially if you want lots to minimize over them than getting just a quantile.
No, that's right. This is also what the practitioners tell us always.
Yeah.
No, it's way more difficult to implement and to deal with, also to explain, because value at risk was relatively easy to explain to the management, and that plays a big role actually in practice. They want to have a nice and easy number, I agree. That's a good point.
Are there any other questions? I think we are almost, we're good on time today. It's perfect. Thank you very much.
Very good.